The last topic we'll look at in this class is solving systems of differential equations. And we'll do this in three parts in three lectures. So this first part, I want to start by just kind of looking at some examples of what systems of equations might look like and where they come from. So a couple of them will come from some applications, and then we'll talk about a couple other ideas. And then we'll look at how to solve a system of equations. So the idea of a system of equations um, can be straightforward as you start thinking about it. Basically, we're going to have multiple solutions we're looking for all at once, and we'll label these like x1 and x2 and so on. And the goal is to find all these solutions simultaneously that satisfy some system of equations. So let me start things out with an example of a common system of equations that comes from one population model. If you have two populations, a predator model or a predator population and a prey, so think like rabbits and foxes or something, predator and prey, the population of each depends on the other. So as the population of the predators grows, they start eating more of the prey and the prey population drops. But then as the prey population drops, then there's food is scarcer for the predator, and so the predator population starts dropping, and then as the predator population drops, there are fewer predators, and so the prey population goes up, and there's this cycling process. And we'll see some of that as we get into more ideas about systems of equations. But this model that we're looking at here is called the Lotka-Volterra model. It's a common predator-prey population model where you have these two populations that depend each on the other. So we have x1 and x2, both of which we'd like to solve for simultaneously. And let's say we call x1 the prey population and x2 the predator population. Then we can build a system of equations by looking at the population of each one. So for the prey population, the rate of change, x prime, is going to be the birth rate minus the death rate, and the same for x2. Now, the assumptions that are built into the Lotka-Volterra model are that the birth rate of the prey just depends on how many there are. So that's like the simple population model we saw much earlier, where you have some birth rate A, some growth rate multiplied by the current population, and then the death rate, you assume it depends on the number of interactions between predator and prey. So the more interactions there are, the more prey get taken by the predators, and that you work out by looking at the product of how many there are of each of them. So that's kind of the assumption of this model, is that the death rate of the prey depends on the product of the two. And then for the predators, the same idea holds. The birth rate minus the death rate is the total rate of change. But for them, the birth rate depends on the food source, depends on how many interactions they have so that they can get food. And so the more food is available, the higher their birth rate. The lower, the less food available, the lower their food rate or the birth rate. And then the death rate, you assume again is just a constant multiple of the current population. So that's kind of the assumptions built into this model. All we're looking at for now is just an example of what a system of equations looks like. So putting it all together, you've got this model where you have x1 prime and x2 prime, and each of them, if you notice, depends on x1 and x2. So there's this linkage between the two solutions. They're closely connected. And I'll write this down, or you'll have this in the notes a little bit later, but this is what's called a coupled system of coupled equations, because they each depends on the other. So there's this back and forth. And so the idea, as you look at it now, it looks like it can get pretty complicated, and it can, but we'll develop some ideas that will allow us to solve systems like this without unnecessary work. So we'll try to minimize the amount of effort. So that's an example of a system of equations where these values are represented. So x1 and x2, the solutions that describe the number of prey or the number of predators at any given time. So those are functions of t, and those are what we're looking for in this problem. The goal is to solve for those two functions. And then a is the birth rate of the prey, b is the rate of predation when they meet, the rate at which the predators can eat the prey. C is the growth rate due to the amount of prey available, and then D is the death rate of the predator. So anyway, the controlling values here are the A, B, C, and D, the birth and death rates, and then based on the values there, this system will behave differently. And so we'll get a chance a little bit later to kind of look at how the behavior of this system depends on these different values. But for now, it's just one example of where a system of equations can come from this interconnected population model. So here's a couple of notes. Again, I mentioned that these are called coupled equations because each rate depends on the other function. So x1 prime depends on not just x1 but also on x2, and x2 prime depends not just on x2 but also on x1. So each rate, each derivative depends on the other function. These equations are also autonomous because they don't depend on t, they just depend on x1 and x2. So they're autonomous, which is helpful for some reasons that we'll look at a little bit later when we talk about what are called phase planes. Those are pictures we can draw for autonomous equations like this one, and we will draw the phase plane for this one a little later. For another example of where a system of equations can come from, here's an example of a mixing problem where we have two tanks, and on the left side you have fresh water coming in at 6 liters per minute into the first tank. The first tank starts out with 24 liters of brine with some amount of salt mixed in, and then there's this back and forth mixing where 8 liters per minute goes from the first tank to the second tank, and 2 liters per minute comes back from the second tank to the first tank. So as you do this, if you notice, that first tank has a total of 8 liters coming in every minute and a total of 8 liters going out every minute through the combination of flow rates. And then the right side has a total of 8 liters coming in and 8 liters going out as well. So the volumes all stay constant throughout this. They're all 24 liters. But if you look closely at tank number 1, for instance, the rate in is the rate coming from tank 2. So since fresh water is coming in from the left, there's no salt coming in that flow. The only salt coming in is the salt carried by the 2 liters per minute that come in from tank number 2. So you have 2 liters per minute times the concentration of salt in the second tank, which is the amount of salt there divided by 24. And then the rate out on the first tank is 8 times the concentration in that first tank. So x1 over 24. And then you can do the same thing for tank 2, where again the rate in and the rate out, you have 2 rates going out, 2 flows going out. So the one coming in is 8 liters per minute coming from tank 1. So that's where you get 8 times x1 over 24. And then the rate going out, you have 6 and 2 both going out with the concentration of x2 over 24. So long story short, it all simplifies down to this final system of equations where you've got x1 prime equals negative 1/3 x1 plus 1/12 x2 and so on, and you have your initial conditions of x1 and x2. So again, if you look carefully at that, the system of equations is coupled and autonomous. It's coupled because each rate depends on the other one, and it's autonomous because there's no t's by themselves on the right side. You'll notice it's a little simpler because we don't have a product of x1 and x2 anywhere, and that's actually going to make it easier to solve one like this using some of the methods we'll talk about later. But we'll leave that for later on. For now, though, just notice that they're coupled and autonomous. If you have a system of equations that's not coupled, then it isn't really a system of equations because you can take and solve each one at a time. If each equation only depends on itself, then you can solve them independently. So really the only systems that are interesting to us are the ones that do have coupling going on. There's one more setup I want to show you, another example of where a system of equations can come from. And this is if you want to solve a higher order linear equation. So the example I'm showing you here is a second order equation, but in theory you can do this with a third order, fourth order, or any other higher order equation you want to do. You can solve by this same approach. And really the equations don't necessarily have to be linear, but we're not going to talk about solving nonlinear systems. So for our purposes, we'll stick to linear ones. So what the trick you use here is that you want to have a system of first order equations at the end of this. So what you do is you create new variables. So I'm going to call x1 just the function y, and then call x2 y prime. Now you notice what happens here is since x1 is just equal to y, x2 is equal to y prime, then y double prime is just going to be x2 prime. So for a second order differential equation, if we set up two new variables, x1 and x2, we can rearrange everything and replace y double prime with x2 prime and replace y prime with either x2 or x1 prime, whichever is more convenient, and then replace y with x1. So that's the setup, and then you have x1, well, using the initial conditions, if y of 3 equals 6, that means that x1 of 3 equals 6, and x2 of 3 equals -1. So you have your initial conditions as well. So what you can see here, what I'm doing is rearranging the equation to solve for y double prime, and then you have replace y double prime with x2 prime, and then replace well, let me show you how this works. So you've got y double prime. This here gets replaced with x2. And then you have x2 equals all of this using x1 or x2 there and x1 here, right? So that's how you get to x2 prime right here. So the idea of the system of equations is we want to have x1 prime equals an equation with no derivatives on the right side, and then x2 prime equals an equation with no derivatives on the right side either. So the convenient way to do it is to have the first equation just be x1 prime equals x2, right? Notice that comes from right here, that x1 prime equals y prime, which is the same as x2. So the bottom line here is, for a system of equations like this, if you had a third order equation, the system would look like x1 prime equals x2, x2 prime equals x3, and then x3 prime would include all the details of the higher order equation. So that would, the information from this original equation is mostly stored within the last equation in your system. And the previous equations are just the including those derivatives or explaining those other derivatives. So let me show you an example with a fourth order one. So here you have a fourth order differential equation, which looks really complicated, but since it's a fourth order, we need 4 variables or 4 functions, x1 through x4. And so you just define them in the same pattern with y, y prime, y double prime, and y triple prime. And again, notice we kind of stop one short of this last one. So this last one is going to be x4 prime. So then the system of equations, the first 3 equations just take this information and port it over here. So x1 prime equals x2, x2 prime equals x3, and x3 prime equals x4. So those first 3 equations are just describing how we've defined our variables, basically. And then the fourth one, x4 prime, you solve for this, the fourth derivative. So you move all this to the other side. So then you have t squared minus 3, and then instead of writing y double prime, we just write x3, and then sine of t times y prime, which is x2, minus 8y, which is x1. So that's the setup for solving a system of higher order equations, which is why we haven't spent a lot of time talking about higher order equations in this class. We've talked about first order a lot and second order a fair amount, but we haven't really addressed any third or fourth order or higher. There are approaches you can use to solve some of those, but more commonly what you'll do is break them down into a system like this and then use the methods we're going to talk about for systems of equations to solve them. So that's why we haven't spent a lot of time on them, because you can do this sort of thing to them. You can also solve these using numerical methods. The nice thing about first order equations is there are things like Euler's method and other numerical methods you can use to solve first order ones relatively easily. So a system of equations you can also solve numerically in the same kind of vein as before. So that's a useful tool to know, how to break down a higher order equation into a uh, system of equations. And once you can do that, then you can approach it using some of the methods we'll talk about to solve systems of equations in the next couple videos.